such activities proceeding even in these pandemic times. These have been difficult times, but somehow technology is making us do things. A few years ago, this would have been impossible to imagine that we will conduct classes. We are also conducting classes. IIIT also is conducting classes online like everybody else. So I'm just going to give you a few thoughts on what has been very current or very big fashion these days of AI. I just give a few thoughts on where we means the whole world has got in terms of artificial intelligence. I am from IIIT Hyderabad. You see the nice, beautiful campus of IIIT Hyderabad on the top. And at the bottom, what you see is a building within our campus called the Kohli Research Block. This was endowed by the TCS Foundation in the name of Mr. F.C. Kohli, who passed away a week ago exactly. This building was inaugurated in 4 years ago. Mr. Kohli himself was present there for doing that. So I start with remembering Mr. Kohli, who has done so much for the entire IT industry. We all won't be here in this position if he hadn't started this outsourced software business for TCS in 1970 or so. And he has been very involved with not only the IT industry, but also education in terms of, IIT Kanpur or COEP Pune. He was a chairperson recently and did great things to the institution. So we'll proceed. So let's look at, I'm glad to see about 170 or so people registered for this event. Even this is an online event. I presume most of them are students. So I've asked them, how do they listen to music today? The answer would be from a phone, tablet, or another electronic device. This would be the way they are listening to music. But think about, even 50 years ago or 100 years ago, the LP record itself was invented in 1950 or became popular in 1950. Cassettes a few years later. So many of us, while listening to music, we somehow got hold of a cassette player when we were in college and would listen to music on that. But even before that, if you wanted to listen to music, you actually have to go to a live program and listen to it and remember whatever you want about the music in your head. There was no recording possible. There's no way to re-listen to it. How many people in the world could do that? Very, very few. Okay. So this the same holds for a play, a dance, whatever. The movie started maybe 100 years ago. The first movies start becoming popular, and we know the history of movies in India or the world, etc. So what made, say, music or many other things so accessible? So-called digital revolution, computer revolution, which consists of multiple things: digital representation, transmission, storage, playback, etc. You do it for music, you do it for meetings, as we are doing now. This is a meeting. We are all located all over the country or sometimes maybe the world. And we are all talking to each other, not as good as sitting in the same room and interacting directly, but still we are able to get a lot done because the digital technology or the digital revolution that came in the last maybe 50 years, 60 years, made it all possible. So what does the digital representation or digital revolution have? It is represent things, whether it's music represented in terms of some sound waves. You use a microphone to capture it into analog sound waves, which will be digitized into some binary representation of music. Maybe the MP3 file is one of the most popular ones, maybe others. Then you can manipulate it. You can remove the music, the noise from it. You can combine two instruments together. You can do many manipulation on the musical file. We all know how to do that. Then you can send it to, you can store it in your file, send it to your phone or send it to your friends. You can send it, and at the other end, you can play it back. There is a, your computer or a mobile phone will allow you to play it back. The sound will be recreated. The digital representation will be converted to analog, and a speaker will create the sound. The same thing holds if you replace sound with a video. A camera will capture it, you manipulate it, and you play it back on a mobile screen or a computer screen or a TV. Similarly, for other things, a document. A document used to be handwritten. Now you can type it, you're represented on a computer as maybe a Word file, and you're sending it, you're editing it, you're printing it on a printer to create a physical thing back. So computers, powerful computers, efficient algorithms, and very creative individuals made all these possible, including this meeting software, electronic meeting software like Skype became popular maybe 20 years ago. It was there, but popular maybe 10 or 15, 12 years ago. Now we are dependent on it all the time. So going back to, you look at industrial revolution time. Industrial revolution, maybe 200, 250 years ago, the goal was to replace or mechanical power of primarily steam engine and other engines to eliminate dependence on human or animal power. Before that, only animals or humans could exert force and make things happen. Okay, and automation started happening due to industrial revolution. So suddenly you could make a lot of clothes, a lot of food, a lot of everything. Things became cheap, safe, efficient, better, etc. Before that, 300 years ago, 400 years ago, the world had probably just enough food, or probably not even enough food for everybody to eat. And most individuals who lived in that time had probably one or two pairs of clothes. You wouldn't have a whole wardrobe of clothes that you wear different ones for different occasions, because this world just could not produce as much clothes, as much food, as much thing. Mechanization made it all possible. Digital revolution and automation of the modern kind tries to do the similar thing for what is considered intellectual tasks. The simple ones are, of course, accounting, calculation, data storage. We may not think of it's very intellectual now, but 50 years ago, if you're in a store, you want to add your account book, you have to add it all yourself. Not even a calculator was there. Okay. And the new machine, the equivalent of steam engine in industrial revolution, is the computer. And it's trying to replace many of the human tasks with, or automate some of the so-called intellectual tasks, or tasks that require our brain. So what are the routine or boring intellectual tasks that we do? Create a financial report. At the end of the day, you want to know what is your, how much did you sell, how much did you spend, and what is the different. Or at the end of the year, you have to create a report that you file with income tax or other areas. Or answer routine questions. If you are a customer service company for a phone company, or a mobile phone manufacturer, or a seller, or you're Amazon, most of the questions are very routine. They happen day after day after day after day. How do I log in? I'm not getting my refund, etc., etc. Answering those questions doesn't really require much intelligence. This is a routine one. Maybe even file a news story, given a point. Some news reporter says, these are the points I want to convey in the story. Now convert into a nice English article, or a Hindi article, or a Malayalam article. That is not a lot of creativity required. Similarly, maybe looking at an X-ray and find out standard anomalies. Drive a car. Driving a car is a routine task, a boring task after you do it enough time. Why do I want to spend my brain energy to drive a car? Can I drive it automatically? Similarly, maybe if you're in education, academia, examination, evaluate examination. Can I get, many of it is not very creative task, so on. So you can do all these into computers doing it will be a good idea. So automation is to make these things also better. Intelligence is to do things that we do with our brain and with AI. So now digital world has created a lot of data, and with that data, with machine learning combined together, you get what is today called as AI. Okay. And what it does is draw huge insights from data. That is the modern AI. Classical AI had tried to model how we do things in our brain step by step, but that was not going anywhere. So what is intelligence? Now there are, you can think of three types of intelligence. Cognitive intelligence, which are like tasks we consider intelligent, like playing chess, playing the game of Go. These are considered intelligent things by us. Okay. Then computers somehow mastered this early. Then there's a perceptual intelligence. I look around this room, or you look around the room, you find 10 people, you can identify how 10 people are there. You can say some are men, some are women, some are children, some people you know. Or similarly about sound, when you hear the sound coming out of your computer, you're converting it into the language and understanding it. Okay, this is the perceptual intelligence. Then next, of course, is what really makes us human is maybe the social intelligence, emotional intelligence, common sense. I don't think the computers are even started to do these kind of things. We don't even know how to attack that problem. AI conquered the cognitive intelligence first in 1997. The computer chess program beat had Gary Kasparov, the then world champion. And today's even a chess program that you can run on your mobile phone, perhaps, or definitely your laptop, will beat the best, Magnus Carlsen or so, or any of the best chess players will stand no chance in front of the best or even the medium-sized chess program today. Okay, that's the improvement that has happened. And perceptual intelligence of looking at camera, looking at the world, or a speaker, a microphone, listening to the sounds, converting into language, understanding it, responding it, etc. That is getting there. Great progress is being made these days. We don't even know how do we approach the last one. Okay. Now there is what typically called Moravec's paradox, which says what is easy for humans are hard for computers and vice versa. So if you look at finding the 27th root of a 100-digit number or playing chess at the level of Magnus Carlsen, these are now very easy for computers. We find it's very hard, so we think they're very intelligent tasks. What is hard for computers and easy for us is just looking at a photograph and say, is there a cat in it? Is there a child in this? What is the gender of this child? Etc. These are very easy for us because somehow our brain does it. We don't know how we do it quite well. We don't know how to articulate it. But computers are finding it very hard to do. Okay. And these are over the evolution, our brains have learned to do these tasks because they're very important for survival. Recognizing a prey, recognizing a predator was very important even for animals. So there's a long history, and also all that is stored in the structure of our brain. Whereas chess and puzzles, etc., probably a few thousand years old, the so-called intellectual exercises. Okay. Now let's look at, say, computer vision, which is the area that I work in, so I understand a little bit. The task of computer vision is understand visual data captured by a camera, just like humans do. Okay. Instead of these two eyes, use two cameras, or one or more, many cameras. What are the tasks? Simple ones like, is it day or night now? Can I recognize objects or people? Can I understand geometric structure? How big is that box? You may not want to know, it's 3 meters long, but we know that it's bigger than the other one, and so on. And look at people and understand the moods of people, the way their face or their body language. You see they're maybe sad or angry or excited, etc. I mean, these kind of tasks that we use our eyes and our visual system to solve for ourselves. Can we do it using the computer? How do we do that? We have to go back to the theories. How do we do it? There is the signals that captured by the camera can be processed using standard signal processing methods. But you have to understand the geometry of projection. What does the camera see? Is the projection of the world, and physics of illumination, optics, cognitive and psychophysical aspects to see how I perceive things in my brain, as well as psychology of the mood of if somebody is sad, what will be there? How will they look? How will they appear? All these we need to fall back on traditional knowledge of all these and somehow give it to the computer and infer it or deduce it from the camera input. Okay, so again, this is combination of large amount of data, very innovative algorithm, very sophisticated mathematics, big computing, and so on. And this is an area that is coming of age now. I'll just show you a few examples. This is a work written by one of my students. It appeared in a conference recently, 2 years ago. There's a problem with playing this. So this is a video. The idea is human capture. Can you look at somebody on the left? They're doing some actions, command action. I want to convert this image or this scene into a 3D model, which will do the same thing. Okay, that's the purpose, and do it without a huge amount of sophisticated equipment. That's why it's called at home. Capture human shape, capture at home. So we put not just a single camera. There's a device called Kinect, which gives not just the view, the image, but also the depth map. Kinect costs maybe 10,000 rupees. Is not a very expensive equipment. So we capture 8 actions performed by say 11 people, simple actions, and then using that single Kinect and some computing, convert them into 3D models so that now later virtual reality or some other computer games, I can transport this person there. Okay, so these are the kind of scenes. They are not very complicated scenes right now. I'll just skip to. So these actions, you need to capture them. Yeah, so simple actions. The people are doing things around, and let's see what do they do. Now these are some of the results. So you on the right side is a model, a 3D model, that a standard model which we fit to this particular person, and this person is not wearing wearing loose clothes, has hair. That's challenge. The challenge is being able to capture in such environments. Okay, and this has been an area worked on by many people. We are, what we did is one more step further. So you can see some qualitative results. Somebody is moving around like this, and you can see the mesh. The right side is a graphics model mesh that also moves around in similar ways. And so now you can take it. You can think of taking it into a 3D environment and put that in a game, or maybe in a virtual reality. Somebody else is seeing you the same way. Okay, so we'll skip the rest of the video. You don't need to watch so much. Now, another work that happened not by my student, but one of my colleagues here and their students has been getting a lot of press recently because it's really innovative. By looking at the video, can you read? Can you understand what they are saying by just looking at the video without the sound? Okay. Lip to wave, they call it. Wave is the sound representation.
Welcome to this demonstration
I hope you can hear the sound.
for learning individual speaking.
Can you hear the sound? Can you hear
Yes,
the computer sound?
Yes, sir.
Okay.
Files for accurate lip-to-speech synthesis. In this work, we try to generate speech from only the lip movements of specific speakers.
We talk about the relationship between the wavelength, the frequency, and the speed of electromagnetic radiation. In fact, the product of the wavelength and the frequency is the speed.
The speech you just is generated solely from the lip movements of the speaker by our lip-to-wave model. We model the generation of speech from lip movements as a sequence-to-sequence problem. Given a silent talking face video, we extract the face in each video frame using a face detector. We feed these sequences of face crops to our spatio-temporal face encoder, followed by a speech decoder. From our generated MEL spectrogram, we employ a standard vocoder to get the raw speech. Even though the main focus of this work is generating speech from lip movements in unconstrained environments, but first, let us check out some results in constrained settings. We also compare our model with some previous works tackling the same problem.
Set white with I7 Set white with I7 suit. Set white with I7 suit. Set white with I7 soon.
Here are the
So what you saw now is the closest other research work which did these things, and the one that these people, our team did, this Prajwal and team did, came very close to the much better than the previous one and very close to the original
results on another data set in constrained settings with a relatively larger vocabulary.
8 pin guns were captured in position. 8 field guns were captured in position. 8.
Oops, sorry. Okay, so that's one work. Actually, this is a corresponding other work by the same team called Wave to Lip. Now, if you give a sound that you want the character to say, the character will move lips in a synchronized way as if they are speaking that. Okay, this is the reverse of that. Earlier, by looking at the lip movement, they're guessing what the sound was, or they're inferring the speech. Now you have the video of some talking head, and you give I want this character to say this particular text. You give the text or a sound, and it'll make sure that the lip moves in a believable way. So both wave to lip and lip to wave. You don't have to remember anything. You can search wave to lip or lip to wave on Google, and you will go to the page that has not only these videos, the original paper, but also the source code. They have created a tool by which you can submit your own video and get sound output, or you can create. You give a video and a sentence that you wanted the character to say. You will create video of that character saying that sentence, etc. So let's look at wave to lip.
Welcome to this demonstration video for our paper titled, A Lip Sync Expert is All You Need for Speech to Lip Generation in the Wild. Please use headphones for a better experience. Let us start by checking out some results from our model.
The framework for our future cooperation. Dear Emmanuel, only 8 months ago,
So this is dubbing.
awarded the
We all have seen movie dubbing where the new language is something that we can understand, but the lip movement is completely out of sync. And that's what you see here also.
prize here at this very place for your enthusiasm for Europe's.
As we can clearly see, the lip movements of the German Chancellor is clearly out of sync with the English translator's speech. Let us correct this by using our proposed model.
The framework for our future cooperation. Dear Emmanuel, only 8 months ago, you were awarded the Pulse Prize here at this very place for your enthusiasm for Europe's.
Let us take a look.
So if you would notice carefully, you can go back on the web and see the video. The lip movement was in sync with the English translation of whatever she was talking in German. Earlier, the English sound was overlaid on top of what her speaking German, so her lips were moving in German, sound was coming out in English. Okay, so this is something that we are very familiar with, and there are many examples. I'll show you some other examples that they on this. This is another similar.
Putin
The French
adds
president,
what he'd like to on the first
originally
issue.
speaking
It's
French,
not for
but
me to comment
lip
on
is
the
moving in
visit of
English.
Madame Le Pen in March.
One of our method's most critical applications can be in lip syncing dubbed scenes in movies and TV shows. Here is an example of Tony Stark speaking the same dialogue in multiple languages.
My name is Tony Stark, and I'm not afraid of you. I know you're a coward. So I've decided. Mein Name ist Tony Stark und ich habe keine Angst vor dir. Ich weiß, dass du ein Feigling bist. Ich habe also entschieden. Mi chiamo Tony Stark e non mi fai paura. So che sei un codardo. Perciò ho deciso. Meu nome é Tony Stark, eu não tenho medo de.
Here
So
is a
let's
clip of
move to Charlie
giving his
Chaplin
famous
speaking
speech in
Hindi.
माफी चाहूंगा पर मुझे बादशाह नहीं बनना मुझे ये सब नहीं करना था किसी पर भी हुकूमत नहीं करनी
We also show an example of a Hindi movie scene dubbed in English with accurate lip sync.
You know it very well. I'm not successful. And I'm not in a position that I can come up to your father and talk to him.
It is possible to have famous professors delivering lectures in local languages with accurate lip synchronization. Here is Professor Andrew N.G. delivering a lecture in German. Also note that our model handles speech generated from a text-to-speech system without any issues.
Das Gebiet der Computervision bewegt sich aufgrund des Aufkommens des tiefen Lernens sehr schnell. Zum Beispiel verwenden selbstfahrende Autos sie jetzt, eine Vielzahl von Dingen zu erledigen.
Another important application of our model, recorded video call.
Shami Bhaiya, I think he was doing rehab and he was bowling at a very 120 wala pace, for us, something na pace pe. But I thought, okay, he's gonna bowl 120 and he promised कि वो मुझे body पे ball नहीं खिलाएंगे.
Our model can be also used for creation of social media content. Here are some things.
Okay, we'll stop here. You can see this creates very believable videos, but you can also immediately see the potential misuse of creating so-called fake videos. This has become a very big problem. You can make anyone say anything. You can make Modi say something, or you can say one leader say something which is so offensive. And now this will also look much better. The lip movement also will sync. So there are, technology is good, a lot of applications. And what we saw recently, the last example is in video conferencing. If your bandwidth is low, you don't have to send the video anymore. You send the pictures occasionally and the sound all the time, and at the other side, you will see the lip moving correctly. But a lot of other misuse also is possible. Okay, so sorry, let me. So this is computer vision. There are many other perceptual tasks which are also being revolutionized by AI. For instance, speech understanding. We all know that today's mobile phones, whether it is, you call it Siri, Cortana, Alexa, Google Assistant, they all are very good. They can understand speech. In fact, they are so good they can understand speech even in Indian languages. They understand reasonably well. They convert it into text, and there is also translation. If you try out, there is a Google Translate app. There is on your mobile phone, or a Microsoft Translator app. You can speak in one language and ask it to translate and play back in another language. This can be very useful if you go to some place and you want to buy something, some place where you don't speak the local language, and you want to buy something. You can talk to the shopkeeper using this interface and so on. Similarly, underlying that, natural language processing, understanding what somebody says, translating to another language, or translating to or understanding truly, so that some database lookup or some other task could be done. The neural NMT, the Skype, they showed speech-to-speech translation in Skype, and this kind of things are possible today. Or very good human-computer interaction. All these are possible. So, in some sense, AI has been AI has been hyped or talked about in multiple ways. I just want to show 3 frames that kind of summarizes AI in so far. First was chess playing like application. We thought that is the ultimate AI. So once the computer does that, it'll be great. So that happened in 1997. And you may have heard it 5 years ago, the best computer program also beat the world champion in the game called Go. The game called Go is a whole lot more complicated with 2 to the power 200 or something possibilities. So it is far more complicated than chess, and humans were reigning champions until 2015 or 16, when the AlphaGo beat the champion. Now, this dream was sold to us: self-driving cars. This is a Google car. There are Tesla car, many others. Now, this is a dream, and this is a huge dream, because if a car has to be on streets of Hyderabad or streets of Thrissur or any street, even the best, most organized streets in California or Germany where everybody drives well, even then there are a million things that it has to handle, which are very, very difficult even for the best of today's computers or best of today's self-driving system. People like to sell you self-driving systems as a marketing ploy, but a car which is self-driving in any way, that can be let loose on the normal traffic, is many, many years away. I don't even know how much. However, what is happening in the last 10 years, 15 years is computers or AI being enhanced perception devices. So the picture shows, you can identify people, maybe recognize them. You can recognize the sounds using a device that you saw on the top. So that is happening. The first thing, chess playing, is happening, whereas the self-driving probably requires the solution of the computer or the AI to be almost as good as we all are, and that may be very, very far away. And there are a lot of worries. People talk about computers taking over, being more intelligent than humans. All that is not going to happen anytime soon or anytime at all. Now, this is the quantitative, the vision. What you saw here is how there is a standard visual task based on this ImageNet library. You can put if you say recognizing cats, recognizing buses, recognizing dogs, recognizing from an image. If you write your own program, create your own system, you can test it on what is called an ImageNet database, and it'll say accuracy will be plotted. So here is the ImageNet, the two contest accuracy has been increasing over the years, as you see here. And this dotted line here is what is considered human performance. You show the same 10,000 images to many humans and ask them to say, is there a dog here, cat here, etc., and see what is the accuracy. They get about 95, 96% accuracy. And many of the computer vision systems started reaching that accuracy, as you see in the time there. Similarly, the speech recognition system, if I speak, English into this system, today's, Microsoft Skype or Microsoft Teams or Zoom, I've not looked at Zoom so much. It can live transcribe what I'm speaking into English, and it'll be, as you see here, 95, 98% accurate. Okay. And again, human performance was reached there. And language translation, which is slightly harder task, the scores are not been, it's not reached. Human level performance is getting reached now, but we can see that the progress has been very heavy, 2.5 to 3.5x improvement in what is called a blue score, which you think of it as the accuracy of the translation. So what facilitated all this? There are three components which made AI and machine learning based AI possible in the last 10, 15 years. That is data, computation, and algorithms. Okay. Now we have large amount of data with internet, with cameras in every phone and everybody carrying it around, with sound recording so easy, with capturing any kind of data being so easy, and internet and storage being able to transmit the data all over. We have huge amount of data. When I was a PhD student doing computer vision 30, 35 years ago, we just had 5, 10 images that somebody collected somewhere and that you could store in your computer. If you have 10 more images, you probably didn't have the space to store them either. So, but you did all your testing on those 5, 6 images. Now, if you want to design a slight improvement on the face recognition, you will have to train and test on 100 million images, without which it won't get any result, good results. Okay, so that is data, and to do all this, you obviously need computation power. Okay, and do all these well, you need good algorithm. So once all this happens, a lot of good things can happen with AI. Medical diagnosis being made faster. You always have shortage of doctors or radiologists, so on. This AI system can help, not necessarily replace them, but help. Okay, and helping the disabled, so blind people being helped in many ways, or any people with disabilities can use computer as a tool to enhance their sensory perception. Right? Public health, looking at outer space, environmental control, whatever. Now, many things. Okay. Now, what is machine learning? I just want to tell you how it's different from what the traditional computer application. A traditional computer application is developed by what it consists of is there is a processor, a CPU or some processor, maybe a supercomputer, maybe a phone computer, maybe a laptop, and the code or a program runs on this processor, and you give it some input, it gives you the required output. This is the traditional computer program. And how do you generate this code? Human programmers will take the specification, what is to be done. This is the task to be done. And you need to know the domain understanding. If you say accounting, you need to know what are the accounting practices. And you will generate. Human programmers will write code, compile, test, this, that, and create code. Okay, and they use what is called an imperative standard programming model, which is embodied by C language, Fortran, Python. All of them are imperative languages. You say do this, do this, do this, do this. And final output is a code that has been hopefully tested well and it works in all conditions. And that code comes here, and this becomes your final system. In machine learning application, things are slightly different. Again, you have a black box kind of system where you give your required input. This is a picture you input here. Output may be the output saying, yes, this has a cat and the cat is in this location. Or this is as a person and person is identified to be Narendra Modi or things like that. But inside, it's not, the view is not processor and code, but a machine learning model. This may be a SVM, support vector machine model, or a deep neural network model, or some other model. And the model is kind of fixed, like a computer has a fixed architecture, model has some kind of fixed structure. The parameters change. Computer runs code, ML model with different parameter values will become different system. And how do you get these parameters? This is called machine learning training of the model, ML training. Again, what is input and output. So you take 100,000 millions of examples of correct input and correct output. So you say, this is the image, here is the face in that image. Here is image 2, here is the face in that image. Here is the image where no face, and output will say there is no face. Like that, so you say, this is the question, this is the answer. Question, answer. Pairs, you create millions and millions of them, and there are sophisticated algorithms that will take this and adjust these parameters, train it for this model, and finally create parameters which work with 95%, 80%, 100% accuracy on similar inputs. And these parameters will go into this model, and then you create this, your final system. So this is a very different kind of model. Input is not your knowledge of what is to be done, but lots of examples where question and answer, that input and output, are supplied together, and the system or the training system will learn the parameters, or will adapt. The ML model will be adapted to that particular question. Okay, so this is a very computationally very expensive process, but intelligence is always costly. Okay, this is our brain and different areas of our brain. But if you look at a human brain, a total human brain has about 100 billion neurons roughly. Okay, and in the cerebral cortex, the front part, this part is 25 billion. But the brain has about 2% of the body weight, very small inside, but it takes 20% of the body energy, but 20 watts of energy is required to run the brain. Okay, and more if you're thinking very hard. And it consumes 25% of the glucose. So brain is an expensive device. You cannot just double the size of the brain. Even evolution could not double the size of the brain without also increasing other things. So it is a lot of computation. And on the right, what you see here is different animals, the ratio of body weight on the x-axis and brain weight on the y-axis. Okay, and typically our visual system is is a very significant component of the brain, because evolutionary vision was used a lot to save ourselves. So that is the architecture. Suddenly, that's a brain. From brain, they evolved this architecture of deep learning. It's called deep learning, or called a deep neural networks or a convolutional neural networks. This was known for many, many years, 30, 40 years. But recently, it was revived because new computers and new data, lots of computation and lots of data made this more useful in real tasks. Okay, and in 2012, not too long ago, a paper came called I talked of the ImageNet challenge, where you are given lots of images and you have to say if this image contains a dog or a cat or an airplane or a sky or tree and so on, many types. That was going, that the accuracy was 70%, 75%, 80% until 2010, 2011. And this team of people devised a deep convolutional neural network. This is the big impact of neural networks came because of this paper, and the accuracy jumped from like 80 to 83% to like 95%, 10% jump, which was not seen very easily. Okay, big jump, and this was facilitated by huge computation. They used the GPU to do the computation, etc. And this deep networks or deep convolutional network were known to people. The people who worked on it in 70s are these three people called Jeffrey Hinton, Jan LeCun, and Joshua Bengio. They alone were using it, was not adopted by others. In late 2005, 6, 8, 10, and once this paper came, everybody shifted to deep neural network for all their AI needs. And in recognition, last year these three were given the Turing Award, or the Nobel Prize of Computing. And so this paper has been cited about 75,000 times in the last 8 years or so. Okay, and what made this possible, along with data, is also computation. So we all know about Moore's law. Moore's law kind of says, not a law, but just a prediction that says the computation power or the chip density will double roughly every 18 months or so. And this was predicted by Roger Moore long time ago. Not long time ago, but 70 or so, 65 or so. And as you see, from 1900 to 2015, this is happening. The y-axis is logarithmic scale. So a line here is like an exponential growth. So this has been holding up. And CPUs are getting faster, but there's this thing called GPU, which is graphics processor units, which we are doing mostly for graphics. Those, but they are very powerful machines. Somebody realized it. They started using it for general purpose computing, and the company like NVIDIA started making faster and faster and better of these GPUs. And that GPU was a critical element in making that AlexNet happen, or to power every AI application now. So NVIDIA itself, the GPU compute power is now 13.4 teraflop on a single GPU that you saw in the previous slide. A thing that you can buy, you can go out to market and buy it. Probably that thing costs, I don't know, maybe $1,000, maybe less than ₹1,00,000, but it will provide you 13.4 teraflops, and you can put it on a large size PC that you may have at home. So you could have it at home. It's not super expensive. Okay. Now that's how AI came about. Now, before I end, I just want to say AI has been, very good, can do a lot of things and will do a lot of things. But it can also, there's a lot of concerns also about AI. The reason being, it can also do a lot of bad things. So one of the concerns people have been talking about is dangerous loss of privacy and autonomy. You are being sensed by multiple devices wherever you go. You carry a phone around, the phone is kind of tracking you all the time. And with a lot of data, a lot of this computation, a lot of this algorithm, will the system take over? Will it become so super intelligent that we will be just slaves to them? Okay. Will AI make humans useless servants? Will doctors, software engineers, teachers, lawyers, administrators, etc., be automated away, that we don't need them anymore? Well, that cannot happen. Some of the things will. So, things like accounting. Every accountant uses a computer now. And you may become, the AI-based accounting system may become also, get resilient to more errors that people make, common errors people make, etc. But the ultimate question is, when you create a machine learning system, what is it learning? I told you you give a lot of input and output combination, and the model will adjust itself parameters to give a good result. What is it learning? Can I explain it? If this system is designing, medicine, giving medicine to a particular patient, are we comfortable that that it doesn't know we don't know what it's doing exactly, but it's saying this, take this medicine or do this process? Are we comfortable? Are we comfortable if that machine is driving on the roads where people are walking around? Will it suddenly kill everybody or many people? Okay. Is the training data good? So there is a whole area of fairness, accountability, transparency of AI system, which is gaining a lot of popularity now because AI systems are there and they're creating problems. So I will just look at a simple example. People have been designing several AI-based computer vision systems. So one of them is look at images and recognize, look at images of people, good, nice images, not, images taken on the streets. Nice images of people and recognize if this is a male or female, the binary gender. The systems are available from many top companies. They are trained using standard models, using the machine learning model that I described. You will feed it thousands and thousands of images. This is where male is there, you will say this is male, female person is there, you say female, no person is there, you say no person, and train it. Now, how fair are the system? Somebody called Joy Bolamini did a systematic study of this for different races of people. So here she created a data set of, I think, 2,000 or so images, which had equal number of people with brown or dark skin and white skin, equal number of men and women. So here, this is all the images, all the dark-skinned men, take all the images, average them together, this looks like it. Similarly, dark-skinned women, fair-skinned men, fair-skinned women. This average face, just to tell you, give a hint of what kind of data was used. Okay, and they run all these three systems, which are made by very well-known companies who really want to be fair. They are not bad or evil companies. Okay, the Microsoft system had 93.7% overall accuracy. Face plus another company is 90%. IBM system had 87.9%. Accuracy means when you say it's a male, it is actually a male, or when you say female, it's actually a female. Okay. Now you split it according to category. all females, black skinned or dark skinned or fair skinned, all males, dark skinned or fair skinned put together. In all males, the accuracy reduced to 8, females 89.3, 78.7, and 79.7, whereas males were 97, 99, and 94. You see the gap, 8% gap between recognizing, males are recognized correctly 8% more times than females. Dark skin and light skin, even more, 12%, 11%, 19% gap. If if somebody happened to be a light skinned person, the accuracy of recognition was much higher than that person had to be dark skinned people. But putting it all together, here it is, the overall accuracy or this error rate is reversed. It's not accuracy, it is error rate. So the larger number means more error. Okay, 37%, 34% error, this is 6% error. You look at this overall total error, 12%, 10%, etc. Male only 2, 6, female 20, 10, 15, etc. All fair skinned people less than 5%, all dark skinned people more than 12, 15%. Fair skinned male, almost no error, 0.8, 0.9 kind of error, as you can see. Whereas the same light skinned female, much higher. Dark skinned male, higher. Dark skinned female, very high. So between light skinned male and dark skinned female, the error, 30% more misclassification. Okay. So it's very clear error increases when more females are included or dark skins are included. And this is just not done. I mean, this is we don't want such system, right? And IBM or Microsoft, they were deeply embarrassed. This is because the kind of data they used, the kind of training they did was biased. You can say the bias is inherited from the world. True, but I don't want a system which does this. This is not just a curiosity. Such systems are used these days. Self-driving cars keep looking at the world and judges if there are people there. Now, if it is not okay, if they say dark-skinned people, they miss 30% of the time, whereas fair-skinned people, they miss only 10% of the time. In accident, you will have more accidents when dark-skinned people are crossing the door. Okay, or there is a real example that somebody had a AI-based soap dispenser. You keep your arm under the soap dispenser, it'll recognize that somebody's hand is there and dispense soap. And there was documented study, black people putting their hand, they will not get soap as frequently or there's more errors for them. Countries like China tracks every citizen through cameras and recognizes and connects them, etc. Many systems do criminal tracking, predict criminality from video, automated driving, automated resume scanning. Many of these companies, you get millions of resumes, so you look for some key elements and select things. These are all using machine learning, black box. So what are they doing is not clear, and we cannot let such systems in the society. So much so that Microsoft and other companies now, recent times, has requested the governments to regulate facial recognition. San Francisco City has banned facial recognition being used in public spaces. So because facial recognition is connected with so many other things, you were there, somebody detects that you were there by mistake, and then if somebody else says, you were found there in a court case, it comes. I mean, all kinds of things can happen. Okay, so I will stop here. In summary, AI is really hot and new, very, very compute hungry. You used to have lots of very big computers, general purpose computers. AI is bringing GPU like special processors into the picture. AI will continue to do many new things, many innovative things, and will touch all our lives in the coming future. There's a lot of hype about AI, but a lot of hope also. Okay, and a lot of things will happen, but you need to be cautious while designing AI applications. This is for people like you and I who will be involved with designing this application, involved with testing them. We have to make sure these are fair, and a whole new area of activity in computer science and social science and philosophy put together is emerging, where you evaluate the fairness, transparency, applicability of such system, which was not there 10 years ago. Nobody thought such an area is required. Now philosophers and social scientists and psychologists and computer scientists are working together to evolve these standards or ways to detect or reduce bias and errors. So I will stop here. I thank you all for your attention and the organizers for inviting me again. If there are any questions that have been typed onto the chat